Hi everyone, and welcome to today's video where we are going to be continuing our journey using Cartesian planes, and today we're going to look specifically at what a translation is. Now, you may not know what a translation is because you may have never heard that word before. A translation is simply just a more age-appropriate version of the word movement or a slide. If you've ever heard the term a slide on a Cartesian plane, that is going to be what a translation is, and that's what we'll be referring to it as from now on as we move into upper grades. So a couple things that you need to understand about translations. The first thing is that a translation is any movement on a Cartesian plane where the image or the original stays the same size and does not change its orientation. Okay, so if this were to rotate, for instance, that would not be a translation. That would be a rotation. If it was to flip itself over, that would also not be a translation, that would be a reflection. So essentially what we're going to be doing is taking this original shape and we are going to be sliding it on our Cartesian plane, and it must maintain its original form. Okay, so it can't grow, it can't flip, it can't rotate. It has to stay exactly the way that it is. The second thing that you need to remember is that when you do your measurements here and solve mathematically the formula for this, each one of the vertices is going to go the exact same distance as each other. Now that might not make a lot of sense, but I will reference that as we move on. So I guess let's get started here. So first things first, what we're going to do is we are going to translate this original shape, so A, B, and C, and I've already put the coordinates here. We're going to translate it so that way, let's say that A is going to translate up here, let's say to 3 and 6. Okay, so I know that this is where A is going to end up. Now, the way that we solve this is we are going to count the number of jumps on the x-axis first, and then on the y-axis, and that is going to allow us to have a little bit of a formula that we can use. So if we start here at x, we're going to be jumping 1, jumping 2, jumping 3, 4, 5, 6, 7, 8. So I'm just going to write that down up here. We're going to say that x is plus 8. And then if we're here at minus 3, we're now moving up 1, 2, 3, 4, 5, 6, 7, 8, 9. So y is going to be plus 9. So that means that A will translate 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, and then up 9. So A translated will be here. Now here's where the formula comes in. This formula right here, the amount of counting that I did for this one step, is going to be exactly the same for each one of these other points. So I'm just going to start off by saying xy is going to be equal to x plus 8, y plus 9. Now, xy is going to be any of these points, and any of these points is going to translate this amount of distance. So whatever it's at x plus an additional 8. Whatever it's at y plus an additional 9. So let's choose C here. C right now is different from A. It is sitting at -4, -5. But I'm starting, this is my starting point, so x plus 8, which means I'm counting 8 spaces over in the positive direction. So there's 1, there's 2, there's 3, there's 4, 5, 6, 7, 8. So 8 will be here on 4, and then it's going to move up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be translating to there. If I take a look at B, sorry, that was C, not B. If I take a look at B, B is here at -7, -5. It's going to move its original space, x plus 8. So it's moving this way on the Cartesian plane as well. So I'm at -7, and I'm going to be moving 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8 will be at 1. And then I'm moving up 9 spaces. So here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I know that that's correct because if you take a look here, B and C are on the same axis. So I know that I've translated that correctly. So my formula, and that's going to look, it's not as straight because, well, I'll do that a little bit different with a little bit different here with this. Make that look a little neater. Be a little bit more professional, I suppose. Caught on my microphone cable. Okay, and B and C are on the same axes. Okay, so we can see that the exact same shape has now been translated over on X and up on Y. But let's say this was our original shape. And let's say we're going to throw some negatives in there, okay? Let's say, we'll go yellow this time. Let's say we want to translate this guy into over here. Let's say we want to translate it here. Now, what can happen is, you can get this a couple of different ways. Sometimes it will say, we want you to translate one of the vertices at such and such a location. So you might get something like A is going to translate to X minus 5, Y minus 1. So if we have these coordinates given to us, we just have to make them happen. So we are going to move over 1, over 2, over 3, over 4, over 5, and then down to 1. So it will automatically translate to there. It made a jump from 3 to 2 to 1 to 0 to -1 to -2. That's 5 jumps backwards, or negative. So A translates there. And then it said down 1. So if it was at 6, it's got to move down 1. So A is now moved over and down. And the same thing will happen if we do it to B. We have to follow these exact same coordinates. We have to follow these changes, these translation changes, because in order for it to stay the same shape and size, we need to do the exact same thing. So if we have B here, and we move it 5 spaces backwards, we're going to go 0, -1, -2, -3, -4, and down 1. We now translate to there. And then if we take a look at C, do we really need to measure C if we think about it? Because if you take a look here, we know that B and C are on the same axis. And if we take a look at the number of spaces in between here, we were at 1 jump, 2 jump, 3 jumps, from 1 to 4 here. Isn't it possible for me to just go 1 jump, 2 jump, 3 jumps, and put my C right there? It absolutely is. So once you've translated a couple of the points, if you can make the shape fit, or make the shape kind of based on what you have, you don't necessarily need to show the math for the rest of it. This is a little bit more difficult doing this vertically. Hang on, let's push that right against the board. Oops. And so that is what translations are. Remembering, we'll do a quick recap, that a translation is always going to remain the same size and orientation. It's not going to grow, it's not going to flip, it's not going to rotate, it's simply just going to slide. So your ending shape will always look like your original shape would have. The other thing that you'll need to remember is when you're showing the work, this formula, this code right here, is going to work for every single vertice. That's why it's not A translate, it's simply XY, because when you look at the new shape, it's going to have an XY coordinate, and you're just applying the X plus or minus if you're moving left or right, and the Y if you're moving up or down. And so this guy right here is going to be key for you to translate everything properly and keep everything in check. So that covers it for translations. If you have any questions, you're more than welcome to leave a comment down below. If something didn't make sense, by all means comment, I'll get back to you. Don't forget to like, share, and subscribe, and we'll check you out again soon when we're going to be talking rotations, and we're also going to be talking reflections. Bye for now.